of the year.
Recording in progress.
And it's my great privilege to introduce today's speaker, Dr. Noam Siegelman. Noam has received his bachelor and master and PhD degrees, all from the Hebrew University of Jerusalem, the most prestigious, the top university in Israel. And then he moved to the US to work in the Haskins laboratories as a postdoctoral researcher. And that's also a great place. If you know about the reading research, that's the lab that starts many legends. So for his work, Noam has continuously been producing great research, and his contribution to the dyslexia research has been recognized by the International Dyslexia Association's 2022 Early Career Award for the great contributions to research. And I have known Noam since he was a PhD student under the supervision of Professor Ron Frost. And I've been hearing so much about this like rising star of a very impressive PhD student. And later on, I have the honor to actually, I have the fortune to actually work with him, collaborating with research. Probably he will share some of those with you today, looking at the relationship between learning and reading, taking a very innovative and interesting perspective as individual differences. And Noam is an expert of combining different research methodologies, including the computational tools, behavioral experiments, and eye tracking technique to explore the mechanisms underlying reading and learning. So I wouldn't want to take up the whole time introducing the great scholarship and leadership Noam has demonstrated, even though he's still a very young scholar. And I'm sure you will see why his research is highly appreciated by many senior researchers in the field, given the innovation and the excellence. So that's just, let me just give the time to Noam and welcome to his research. Noam, the floor is yours.
Thank you so much, Denise. This was an incredibly kind introduction, and I'm really hoping that I can live up to it in my presentation. I will do my best. Thank you again for having me. It is really a great honor. I saw the list of speakers and the list of talks, and I must say that going through the virtual psycholinguistics forum previous talks, I just have so many things that I want to go back and listen to now. And it is a great honor to join this very distinguished list of speakers that you already put together. So let me just share my screen. Okay, I hope that you can all see my slides. So
we are still waiting.
Oh, sorry about that.
A little bit.
Yeah. Do you see my slides?
Not really.
No? Oh.
No,
yes, I can.
Oh, okay.
Oh.
I can too.
Oh, sorry about it. Maybe try again.
Okay, let me try again. I hope that you can all see it now.
Yes, I can.
Okay, perfect. Thank you. Okay, so the topic of my talk today, as Denise already mentioned, is reading. And specifically, what I'm going to do is to tell you about a very interesting process that reading research has been going through. Essentially, the fact that in recent years, more and more people now see reading and reading acquisition essentially as an exercise in statistical learning. And this new perspective created a renaissance of sort in the study of reading, both because it kind of promised a new way for understanding reading, but also because now we can try and use reading as a test case, providing potentially insights for a broader phenomena, the phenomena of regularity extraction more broadly. I see that there's a raised hand. Is everything okay? Okay. If there are any technical issues, please let me know. Yeah.
Right. I guess.
And today specifically.
Sorry.
Yeah. Okay. No, that's fine. And today specifically, I will try and unpack the potential implications this new statistical learning perspective on reading has to the study of individual differences. So I will start by presenting a series of studies that essentially ask, what can this new perspective tell us about success or failure and the determinants of success or failure in reading acquisition? And then I will try to go back and ask, what can we learn about statistical learning abilities more broadly from this particular test case of reading and individual differences in reading? But of course, before I can tell you about reading as statistical learning, I kind of need to take a step back and make sure that we are all on the same page with regards to just knowing what statistical learning is, right? So let me just start by defining statistical learning, which is the mechanism by which cognitive systems extract regularities from sensory input to discover its underlying structure. And in the last couple of decades, statistical learning really has become this major theoretical construct across domain in the cognitive sciences. And the reason for that, I believe, is that now we can think about multiple aspects of different sensory inputs essentially as those complex sets of statistical regularities, those complex statistical creatures. And since statistical learning is essentially the mechanism that enables us to extract such regularities, statistical learning is now considered to play a very important role across many cognitive domains, from language learning and use, both spoken and written, to motor learning, to scene and object perception, to attention, to our ability to learn and appreciate music, to some aspects even of our social life, etc., etc. And this is just really a non-exhaustive list. So for example, if we go back to our test case for today, sorry about that. If we go back to our test case for today, the test case of reading, the reason why so many reading researchers are now really interested in statistical learning has to do with the fact that writing systems can be thought of essentially as comprising a complex set of statistical regularities. So for example, all writing systems of the world represent the spoken language, and you can essentially think about the mapping between printed units and sounds as one that comprises complex quasi-regularities. So for example, in English, the sequence of letters EA typically is pronounced as E, as in the word beam or near, but it can also be pronounced in a lower probability as the sound E, such as in the words head and pearl, and in an even lower probability as the sound A, such as in the word stay. This is just one example. There are also other more subtle statistical regularities that exist in this mapping between print and speech. So I'm going to do a short demonstration. Since we are in Zoom, I don't expect you to unmute yourself or anything, but just try to do this yourself, okay? I'm going to present a sequence of letters on the screen, a non-word sequence of letters that has no meaning. And I just want you to try and pronounce it out loud, okay? You are muted. I will not be able to hear you, but this is for a demonstration for the sake of you, okay? So it's going to be presented on the right side of the screen, okay? Are you ready? Try to pronounce the following sequence of letters, 1, 2, 3. Okay, good. So I'm assuming you all had some spoken response to yourself. And now I'm going to have to present to you another sequence of letters again. Just try to pronounce it to yourself when you're ready. 1, 2, 3. Okay, great. So I don't know if it actually worked, this demonstration. It sometimes does and it sometimes doesn't. So these two sequences of letters, right, they have the same grapheme EA, right? But I'm assuming that many of you pronounce the CHEAD example as ched, whereas all of you, or the vast majority of you, pronounce the CHEAM as chim. And the reason for that can be kind of traced back to complex statistics that exist in the writing system. That is the fact that before M, the sequence of letters EA is typically pronounced as E, but before the letter D, the same sequence of letters is typically pronounced as E. Now, in addition to those regularities that exist in the mapping between print and sound, there are also regularities, quasi-regularities between print and meaning. So for example, all those words, farmer, trader, and fighter, have something similar in terms of their print, as well as in terms of their meaning. But again, this is a quasi-regular system, so corner is not someone who corns, right? And lastly, there are also regularities among the printed units themselves. So for example, if I present to you those two sequences of letters, one of those sequences look more like an English word than the other, and presumably this has to do with what letters co-occur in the language or not. And lastly, if I present to you this sentence, you have pretty strong expectations regarding the upcoming printed units, both because of the semantic message, but also because simply of the co-occurrences of printed words in the language. So all these examples essentially demonstrate the potential richness of the sensory input when it comes to writing systems. But of course, what they don't tell us, or don't tell us necessarily, is how we can demonstrate in the lab, as experimentalists, a link between statistical learning and another cognitive function of interest, in our case, reading. And there are many possible ways to go about this, but one possible avenue comes from studies of individual differences. The idea is that if we can show that individual differences in statistical learning predict individual differences in our outcome, in our case, reading, this can demonstrate a theoretical link between the two. So with this very, very simple idea in mind, we as a field kind of converged to a very simple experimental approach that we use in order to test the links between individual differences in statistical learning and other outcomes. So what we typically do is we sample a group of participants, we bring them to the lab, and in the first step, we simply measure their statistical learning ability. Typically, we do this by using some canonical, typical statistical learning tasks, let's say the visual statistical learning task that you may have heard about. This is a task where we first expose participants to a long stream of shapes. And the idea is that this stream is not completely random, but rather it actually consists of some co-occurrent patterns, some shapes that like to appear one after the other. This typically goes for about 10 minutes. And after this is done, we expose participants to a test phase where we ask them, which pattern are you more familiar with? Either this one or that one. And the idea is that only one of those patterns actually constituted a pattern, a repeating pattern, had higher transitional probabilities between shapes during the exposure phase. We can also use an auditory statistical learning task where instead of having those visual shapes, we can present participants with a long stream of auditorily presented syllables. And again, this is not a random stream, but rather it consists of some syllables that like to co-occur together. And again, in a test phase, we typically ask participants which word belongs to the language you just heard. Either a word that consists of 3 syllables that appeared together in this order during the exposure phase, or a series of syllables that occur during the exposure phase, but presented in a different order. In the second step, after we measure participants' statistical learning ability, we simply measure individual differences in the outcome of interest, in the cognitive skill of interest. In the context of reading, we will typically do this by using some standardized measure of reading skill. And now when we have scores for each participant in their statistical learning ability and scores for each participant in their outcome, in our case, reading skill, we can simply measure the correlation between the two. And again, the point is that if we see a positive correlation between statistical learning and the outcome of interest, this will strengthen the theoretical link between the two. So at this point, you may wonder, well, do individual differences in statistical learning predict reading skills? And if you look at the literature, the common answer that you will get to this question is a yes. Because during the last decade or so, there has been some studies indeed presenting evidence for a positive correlation between statistical learning skills and reading skills. But as always in science and in life, things are not that simple. If you look at the literature a little bit more carefully, one thing that you will notice is that the magnitude of correlations is quite variable, more than what you'd expect based on sampling error alone. And also the correlations are generally quite small, which is perhaps surprising from a very strong statistical learning perspective of reading. And in addition, and perhaps more concerning, there also have been more and more recent null results, essentially studies that fail to show a positive link between measures of statistical learning and measures of reading. And again, as a side note here, I will say that I'm using, again, reading as my test case and my topic for today. But I think that this mixed finding situation is kind of true for other domains as well, the link between statistical learning and other cognitive outcomes. So in a lot of my research, what I try to do is to understand what is going on here, understand what can explain this mixture of findings that we see in the literature. Or in other words, what are some of the challenges that we face when we study individual differences in statistical learning and their relation to other outcomes. And like in many cases, I believe that some of those challenges are methodological and some of those challenges are theoretical. So when it comes to methodological challenges, we still have this problem where common statistical learning tasks are often, not always, but often not suitable for measuring individual level performance. These are tasks that originally originated from group level studies, and they are simply not precise enough, reliable enough to estimate individual differences in a reliable and valid enough manner. And we try to mitigate this issue a little bit by improving typical statistical learning measures, simply applying what we know from psychometrics on these typical statistical learning tasks, making sure that we have enough items in the test, that they are varying in the level of difficulties, etc. And of course, once we do that, we get to better measures of statistical learning at the individual level. And in addition, we also try to offer additional measures, essentially measures that look not just after learning has occurred in some ad hoc, post hoc test phase, but actually gain some measurement during the exposure phase itself. For example, we developed this very, very simple self-paced visual statistical learning test where we simply ask participants to advance the stream of shapes. Every time they want to go to the next shape, they press a button. And simply by taking reaction times, we can get a reliable measure of learning that gives us some insights regarding the trajectory of learning throughout the exposure phase. Now, if anyone's interested, I can, of course, talk about those methodological challenges forever, and I'm happy to take any questions about them. But today I want to focus more on the theory. And specifically, I want to highlight the fact that even if we deal with all the methodological challenges that we have, we still need to face a lot of big theoretical challenges. And I think that all of them essentially boil down to the fact that we still have a limited understanding regarding the computations that are involved in different statistical learning tasks, and a limited understanding of how they actually relate, how those computations actually relate to different cognitive outcomes that we care about. Again, in our example, reading. In a series of theoretical papers, together with Ram Frost, my former PhD supervisor, and Luisa Bochertz, my dear colleague, we've argued that the vast majority of studies took what we call the black box approach for understanding the role of statistical learning across cognition. They essentially demonstrated that statistical learning, treated as this one big black box, a uniform construct, has something to do with a variety of cognitive outcomes that in these studies were treated essentially almost interchangeably. Now, this approach, although it looks very intuitive and nicely simple at first, suffers from two challenges. The first, on the left side of the equation, is the fact that statistical learning, if you look at recent data, we have more and more data suggesting that it's actually not a uniform construct. Specifically, individual differences patterns reveal effects of modality, domain, and information specificity. For example, if you think back about those two tasks that I showed you before, the visual statistical learning task and the auditory statistical learning task, apparently the correlation between them is close to zero. So there's patterns of modality specificity when you look at individual differences, which means that the task that you're going to choose for your study is going to impact drastically the outcomes that you're going to get. Similarly, there are differences between tasks that measure performance in verbal materials and non-verbal materials. We've argued that, unsurprisingly, this has to do with the fact that when we learn verbal material, we already have a lot of prior knowledge that we bring about to the task that influences the outcomes, the learning outcomes, and we have less of those biases and prior knowledge when we learn non-verbal material. And there are also important differences between learning distributional and learning transitional statistics. That is, learning the frequency of different elements and learning what comes after what, the probability of B given A. In addition to those patterns of modality, domain, and information specificity, we also have good reasons to believe that the other side of the equation is also quite complex. And this is due to the fact that statistical patterns in different cognitive functions, they differ quite substantially. And as a result, it is unclear whether there are indeed some overarching statistical learning computations that are involved regardless of the domain. Essentially, in a recent paper led by Luisa Bochertz, we've argued that it is still unclear whether there's indeed this general statistical learning factor on which different domains are loaded, that is in the brain or at the computation level is instantiated by some central device, or whether there's instead specific statistical learning computations, specific statistical learning machineries that are instantiated using different computational principles that are specific to different domains and that are meant to capture the regularities that are essentially encompassed in different domains. So what does it all mean? So given that statistical learning is not this big black box, that is, it is not a uniform construct, and given that the statistical computations that are involved in different domains might be in fact quite different, how can we nonetheless investigate the link between statistical learning abilities and any domain that we care about? So what I'm going to offer in the rest of this talk is kind of an alternative approach. And the idea would be that instead of using some artificial statistical learning task and examine its correlations with some outcome that we care about, what we're going to try and do is to look at the outcome itself, but try to analyze behavior in the outcome from a statistical learning perspective. So in a way, kind of forget about these artificial statistical learning tasks for a bit. And again, unsurprisingly, I'm going to do this using our test case, the test case of reading, and specifically, I'm going to focus on quite early reading skills, focusing on literacy acquisition, where we know a lot of individual differences exist between children. So I'm going to talk a little bit about the series of studies presenting this statistical learning view of individual differences in reading acquisition. All of these studies were done during my time at Haskins Laboratories with many colleagues that I will mention, and you will see their names, but especially with my postdoc advisors, Jay Rickel and Ken Pugh. So just to make sure we are on the same page, what is it that we're trying to do here? We are still trying to explain individual differences in literacy skills, specifically in early literacy skills. But now our predictor is going to look quite different. Instead of using those artificial statistical learning tasks that are predictors, we're going to try and look at individuals' sensitivity to different types of statistical regularities by examining their actual reading behavior. And really the key phrase here is their actual reading behavior. And of course, this approach kind of opens up a series of questions that we now need to answer. Well, first, we need to understand, well, what are the relevant regularities that exist in writing systems and how do they actually shape the organization of the reading system? We need to understand, well, how can we quantify these regularities so we can study them experimentally in the lab? We need to see, well, whether readers indeed differ from one another systematically in their sensitivity to these different regularities. And lastly, if we indeed see such variability, we need to understand, well, what are the implications of this variability for understanding variability in reading skills? Okay, so let's start with the first question. What are the relevant regularities in the reading system that shape the organization of the what are the regularities in the writing system, that shape the organization of the reading system? And in order to answer this question, we took inspiration from a foundational, very important model in the field of reading, the triangle model of reading, that I'm sure some of you have heard about. So the triangle model of reading says something that is beautifully simple and has immense explanatory value. It essentially says that knowing to read words is essentially knowing to associate printed units of the language, let's say the sequence of letters BIN or the orthography of the language, with the sequences of sounds that those sequences, the orthographic sequences, represent. So in this case, simply the sequence of sounds bin or the phonology of the language, as well as with the meaning that those sequences represent. So in this case, just this object in the world, right? The semantics of the language. So again, knowing to read words is essentially knowing to associate orthography, phonology, and semantics, print, sound, and meaning. Now, importantly, from a learning perspective, the mapping between print, sound, and meaning is not arbitrary, right? There are quasi-regularities that exist in these mappings, and over the course of literacy acquisition, we can learn them and then utilize them to read more efficiently. So we already talked about the regularities that exist in the mapping between print and sound. So again, think about words such as bin, mint, mist. They all have something similar in how they are written and also something similar in how they sound. But again, this is a quasi-regular system, so pint is an exception, right? And similarly, there are those quasi-regularities in the mapping between orthography and semantics. Farmer, trader, and fighter all have something similar in terms of their printed forms as well as their meaning. But corner has the same form, but a different meaning. Great. So now we've identified some key important foundational regularities that exist in the writing system, and we believe that they shape the organization of the reading system. Then the second question is how we can actually quantify these regularities so we can study them experimentally. And let's start with the regularities between orthography and phonology and sound. So the way that we typically go about this we simply collect a large-scale corpus of many words in the language that we care about. In this case, it's going to be English, because I'm going to present work in English predominantly in this talk. And we have both their orthographic forms, their printed forms, as well as their pronunciations. And once we have this corpus, we can then start to quantify different types of measures that capture the correspondences between the two. There are many different measures that you can come up with. In a paper a couple of years ago, we've argued that information theoretic measures are particularly useful when it comes to quantifying this mapping between orthography and phonology, because you can use a measure such as entropy to quantify the extent of uncertainty that is implicated by a given orthographic unit. For example, you can capture the fact that EA in English implicates more uncertainty regarding its phonology than EE, because EA can be pronounced in multiple variable ways. And you can use a measure called surprisal to quantify the extent of unpredictability in a given orthography to phonology pairing. So, for example, capture the fact that pint is more unpredictable than mint. But for the purpose of the work that I'm going to show you in a couple of slides, I actually used a very, very basic measure, trying to capture the most basic regularities that exist, which is simply the surprisal of the vowel grapheme to phoneme in English. So, for example, if you have words such as mint, we look at the surprisal of the vowel I, the printed vowel I, being pronounced such as the sound right? Simply taking the probability of this value and minus log of this probability to get us to surprisal. So more unpredictable is higher. Okay, great. So now we've quantified orthographic to phonological regularities, and we have some measure to capture those regularities. What about the other side of the triangle? What about the regularities between orthography and semantics? Well, how we can actually quantify these? Well, when we started this project a couple of years ago, we thought that this is a little bit tricky, right? It's not that trivial how to quantify this shared meaning that trader, fighter, and farmer have, but not corner, right? This is not that trivial how to do that. So when we started this project, we said, well, let's just start with some very basic proxy of semantic influences. And specifically, we focused on a measure called imageability, which is defined as the ease of eliciting a mental image, which we know impacts group level reading quite robustly. That is, so for example, bin is more imageable than the word such as hope, because it's easier to imagine bin, it is more concrete, than to imagine hope. And again, I want you to keep in mind that this is a very primitive proxy that in fact captures what we believe are inefficient orthographic to semantic cues, because imageability by itself does not actually provide a reliable and efficient way to map printed units into meaning, right? It does not actually capture the real regularities that exist in the orthographic to semantic mapping. Again, think about this fighter, farmer, trader, but not corner example that I showed you before. Okay, so keep this in mind as we go along, and we will go back to this in a few slides. But for now, we have those two measures. And the next thing that we wanted to do is to quantify individual differences in reliance on those two sources of information. So we had a sample of about almost 400 kids in the 2nd to the 5th grade, and they all participated in a word reading aloud task, simply presented with one word at a time and needing to pronounce it out loud. And this task had 160 trials. And importantly, we selected items to this task such that they vary along those two critical dimensions. So items varied continuously in how regular were the orthographic to phonological associations, again, using this measure of the surprisal of the vowel grapheme to phoneme from words that are more predictable in terms of their phonology, such as bin, to words that are less predictable, such as child. And words also varied in terms of their imageability, from imageable words such as dog to less and less imageable words such as verb. And given that we had this variability in our design, we could now estimate for each child, for each participant at the individual level, to what extent they rely on each of those two sources of information. Statistically, this was simply done by extracting slope scores from a logistic regression model estimated for on the data of each child, quantifying the relation between accuracy in each child and those two item properties. And the idea is, again, very simple. The idea is that if a child reads correctly words that are increasingly more regular in terms of the orthographic to phonological associations, this can be taken as evidence for this child's reliance on orthographic to phonological regularities during word reading. But if a child reads correctly words that are increasingly more imageable, this can be taken as evidence for this kid's reliance on orthographic to semantic processes, again, this inefficient semantic cue. Okay, so let's look at some data. I'm just going to take a sip of water with your permission. Okay. So what we have here is essentially a plot with the 399 kids that we had in our sample. Okay, so each point in this plot is one child. And the x-axis, these are already slope scores reflecting sensitivity or reliance on orthographic to phonological regularities. The slope scores reflecting the impact of our surprisal measure on accuracy. And the y-axis is again a slope score again, but this time reflecting sensitivity or reliance on imageability. And there are a couple of things that you can see from this plot. So first, you can see that on average, there's above zero reliance on both of these dimensions. These are represented by the dashed lines that are higher than the solid lines significantly. Okay, so in both dimensions, there's above zero reliance. That's not surprising. That's very consistent with group level studies. You can also see that there's overall a small negative correlation between those two dimensions. So overall, there's a slight tendency for kids who rely more on orthographic phonological regularities to rely slightly less on imageability and vice versa. But you can also see that this is a very weak correlation, and perhaps the most important thing relatedly is that there's a lot of individual differences, right? So individuals are kind of all over this two-dimensional space, right? Now, of course, the most important question now is going to be, well, does this variability actually going to predict reading skills? Right? So in order to show you this data, I'm simply going to add colors to this plot, reflecting success in a standardized measure, in this case, of word reading. And this is the results that we got, okay? So red points are kids that got higher scores in the standardized measures. In the standardized measure, blue points are kids that got a lower score. And this is, by the way, raw data, okay? And you can really visually see the results, right, from the raw data. So essentially, kids who rely more on orthographic to phonological regularities that are more on the right side of this plot seems to have higher word reading skills. And similarly, kids who rely less on imageability towards the bottom portion of this plot also have higher word reading skills, right? And I'm presenting here the results from the with word reading standardized measure as the outcome, but we are getting very consistent results regardless of the outcome measure that we look at. Okay, so what does it all mean? Well, it seems that individuals indeed differ in their reliance on orthographic phonological regularities and imageability during word reading. I just want to mention here and stress here that these are individual differences that could be identified because we actually looked at reading behavior itself, right? It would be very, very hard to identify those individual differences by using some artificial statistical learning task. Right? And it seems like these individual differences are strongly associated with early reading skills, where individuals who rely more on orthographic phonological regularities and rely less on imageability are those that are better readers. And I also want to mention here, if you are interested in intervention or in educational psychology, and perhaps some of you are, we actually had follow-up work where we tried to use those two dimensions to predict not concurrent reading skills, but future reading skills after phonics, orthography to phonology focused intervention. And what we saw, perhaps a little bit, it's a bit of a depressing story, but still a statistically robust one, is that those two dimensions predicted future reading skills, but they did so where the rich got richer. So essentially individuals who were higher in their sensitivity and their reliance on orthographic to phonological regularities and lower on their reliance on this inefficient cue were those who gained more from the phonics intervention. Okay. Now, I do want to go back to a point that I mentioned before, which is this important point that imageability does not equal orthographic to semantic regularities. Because as I mentioned before, imageability does not provide an efficient cue to map printed units into meaning. It does not actually capture the important, reliable, quasi-regular mapping that exists there, right? Again, think about this farmer, trader, fighter example from before, right? And the next thing that we wanted to do is actually capture those regularities that exist in this mapping. And in order to do this, what we had to do first is to quantify the consistency that exists in this mapping, to what extent different words are consistent when it comes to these actual regularities that exist in the mapping between orthography to semantics. And we did so by relying on great work by Marco Morelli, Simona Armente, and their colleagues with some methodological improvements that I will not get into today. But essentially what we do in order to quantify orthographic to semantic consistency of a given word is we start by defining a word's orthographic neighborhood. So for example, if you have a word such as cat, the neighborhood of cat is going to be many words that are similar to it in terms of their form, so words such as bat, mat, can, etc. And then we use distributional semantics, essentially word embeddings, word vectors, to examine the semantic similarity between each word and all of its neighbors. And then from this, we simply have a measure of orthographic to semantic consistency of a given word, which is simply the mean semantic similarity of a word to its neighbors, right? And the idea is that if a word is more similar semantically to words to which it is similar orthographically, this means that this word is more consistent in the mapping of orthography to semantics. And now that we have this additional metric, this word level metric, each word telling us how consistent it is in the mapping between orthography to semantics, we can go back to our child word reading data, simply rerunning those individual differences models, and now extracting a slope score also reflecting reliance on orthographic to semantic regularities, those actual regularities that exist in this mapping. And importantly, what we now see is that sensitivity to orthographic to semantic regularities is actually positively associated with reading skills, specifically with comprehension skills. So what you can see in this figure is that sensitivity to orthographic to semantic regularities here on the y-axis positively predicts comprehension skills in this particular case in the same direction as reliance on orthographic to phonological regularities, but importantly in the opposite direction as reliance on imageability. Okay, so what does it all mean? Well, it seems that good readers are those who rely more on orthographic to phonological regularities, rely less on this inefficient semantic cue imageability, but rely more on the actual regularities that exist in the orthographic to semantic mapping, this measure of orthographic, captured by this measure of orthographic to semantic consistency. And I think that, to me, this was quite interesting because it kind of made me rethink the theoretical link between statistical learning and reading. I started this talk by presenting a very simple promise that made so many reading researchers excited about statistical learning, which is this idea that perhaps better readers are those who are simply better at learning regularities from the input period. But I think that what our data suggests is something that is a little bit more subtle and refined. It essentially suggests that perhaps better readers are those who can rely or who know to rely more on efficient sources of information and rely less on arbitrary, inefficient sources of information. So essentially, the idea is that the written input, and many other inputs as well, consist of multiple types of cues and multiple types of quasi-regularities. And essentially, good readers are those who know how to balance the impact of all these sources of information, given how efficient they are for solving the task at hand. Now, of course, this is at this point mostly an hypothesis, and we are doing a lot to test that. And in many ways, the work that I just presented is, of course, just the tip of the iceberg. And I want to tell you a little bit about some of the directions that we are now going with this. So first thing it is that we're trying to do, of course, is to go beyond the types of regularities that I just talked about. We just started to explore these very basic types of regularities. But of course, again, the whole point is that writing systems potentially contain a plethora of potentially relevant, often very subtle types of regularities. And what we try to do now is kind of to explore these additional types of regularities, both at the group level, but mostly at the individual level. So for example, one thing that we do is to go back to those actually more subtle orthographic to phonological regularities that I mentioned, these context-dependent regularities. And this we actually do by using non-word reading tasks, much like the one that I showed in the demonstration before, presenting items that are essentially ambiguous in their pronunciation, words such non-words such as cheat, chad, kit, cat, von, vown, pont, pont, von, von, right? And importantly, I will not get into the details, but we try to first, again, quantify the written input statistics, coming up with a measure that essentially reflect the extent to which a context-dependent versus an independent response is supported by the written language statistics. So if you think of CHEAD, to what extent the corpus written statistics pushes you toward shed versus cheat. And once we have this measure, again, we can now use it to extract slope scores, reflecting to what extent different readers, different children actually rely on these very subtle types of context-dependent regularities in the writing system. And what we see is that indeed, this sensitivity to context-dependent orthographic to phonological regularities predict reading skills, and it does so by predicting something extra above the regularities that we looked at so far. So this is one type of work that we're currently doing, looking at more subtle types of regularities that exist in the mapping between orthography, phonology, and semantics. Another thing that we're doing right now is to go beyond the single word level. Right? So essentially, all the work that I presented so far have to do with regularities that exist in the mapping of orthographic units at the level of the single word to phonology and semantics. But when we think of full sentences, right, if you need to read this sentence that appears here on the screen, you have many other types of regularities as well, not just the regularities that exist between the different printed units and phonology and semantics, but also essential regularities that exist within the printed complex printed orthographic message itself, both within a word and across words. Once we do in this work, we mostly rely on eye tracking as our methodology, because most of these regularities exist at the level of sentences and texts, and the outcomes that we want to look at, the behavioral outcomes, have to do with how people move their eyes across those more complex information structures. So just to give you one very brief example, and I see that I need to go fast. My very talented master's student, Kobe Raz, has been working on a measure that essentially quantifies uncertainty in what we think of as lexical convergence. And this is a measure that tries to quantify that given where participants actually land, fixate on a given word when they read text. So for example, if you have the word lexical, as we saw before, we have some assumptions regarding visual acuity in different letters of the word, given where a participant actually landed in a given trial. And we apply some perceptual filter, and from that, we do what we think of as the hangman quantification. Hangman, for those of you who know the game, right? This is essentially a process where we assume that a participant in its trial, given some constraints of visual acuity, was able to identify some letters, but not others. And from that, essentially we can list the different lexical candidates that the participant had in this presumed trial, this presumed fixation, to obtain their frequencies, and from that to compute entropy. And this is a process that we repeat many, many, many times until we have essentially, for each word at each fixation location, an estimate of how much entropy the participant is going to have regarding lexical convergence. And what we see, quite interestingly, is that as we see some evidence for quite sophisticated reading behavior, we can see that we see that when participants land in a place that has a lot of entropy regarding a lexical convergence, there is a lot of uncertainty, they essentially tend to fixate for shorter amount of times in their first fixation on that location. And instead, what they do is they refixate and they look for information elsewhere. So good readers are those who do this very sophisticated reading behavior when they land on a place with a lot of uncertainty, they disengage from it quickly and they go to look for information in other places. Now, of course, this is quite preliminary, and what we do now is we look at ongoing work, essentially looking at the interaction with other types of regularities, both orthographic to phonological, orthographic semantics, and also other word level predictability. And we also, of course, look at individual differences, and we have some interesting preliminary data that if anyone is interested in hearing some speculations, I'm happy to talk about. The other way in which all this data that I showed you today is simply the tip of the iceberg is because we are simply looking at a very, very, very small part of what can be thought of as a big space that we still need to explore. And this space can be divided in at least two dimensions. The first is the developmental dimension. So all data that I showed you so far comes from a very particular point in development. And of course, when you think about development, the reading task changes, right? Young kids read mostly isolated words. Older individuals like ourselves read mostly continuous texts for comprehension. And also the input changes, right? So from a statistical learning perspective, you would kind of expect a developmental shift from reliance on more simple regularities, mostly that have to do with the mapping of orthography to phonology and semantics, to more and more and more reliance on increasingly subtle regularities, both in the mapping between orthography to phonology and semantics, but also in the orthographic domain itself. And this is one thing that we explore. And again, we look at individual differences in each of those developmental stages. The other very important dimension, of course, have to do with cross-linguistic differences. The nice thing about cross-linguistic differences in reading is that essentially they can be thought of as some sort of a very, very nice natural experiment that we have in statistical learning, because each writing system adopted a different way to represent phonology and semantics, as well as orthographic uncertainty in its writing systems, in its writing system. And we can now quantify these different types of regularities and ask how this different mix of regularities that each writing system presents to its readers impact the types of regularities different people are sensitive to, again, not just at the group level, but also at the individual level. And again, the idea is that perhaps one type of regularities in one writing system is going to be a very good thing to rely on because it's very efficient, but the same type of regularities may be less efficient in another writing system. And I will mention that, of course, if we need to do good, high quality work on cross-linguistic differences, of course, we need data for many, many languages, reading data for many languages. For that, we actually have the multilingual eye movement corpus, which is a resource, an open data resource that we assembled myself together with Victor Cooperman and many of our colleagues, including our dear colleagues in Taiwan. And essentially, this is an eye tracking, eye movement database, open, publicly available. So anyone who's interested in doing cross-language reading research can use this eye tracking passage reading database. And now we are using this in my lab to look at those questions about the information structure in the input in different languages and how it impacts in eye movements in different languages. So for the few minutes that I have left, I want to take the liberty to speculate a little bit. Because as I mentioned, you can really think about this link between statistical learning and reading as kind of as a two-way street. We can gain a lot of insights into reading from applying this statistical learning perspective. But potentially, if reading is an exercise in statistical learning, you can use it as a test case and ask, what does it tell us about statistical learning and regularity extraction abilities more generally? I started this talk by presenting the original promise of statistical learning research to understanding complex high-level behaviors. Perhaps the reason why so many people are excited about statistical learning. And this is a fact that statistical learning offers this very intuitive, simple notion that complex behaviors can be thought of essentially as the outcome of a simple process of regularity extraction. And I think this is true at some intuitive level, but I also think that our data suggests a somewhat updated or refined version, where the idea is that sensory inputs in all domains contain a plethora of regularities to be learned, and potentially complex behaviors emerge when the cognitive system is organized according to the systematicity of different regularities and different sources of information. And this is an idea that can be applied across multiple domains, not just in the context of reading, as we started doing, and not just in the context of other aspects of linguistic behavior, but also in other non-linguistic domains whatsoever, from motor to learning to face recognition to scene and object perception, attention, etc., etc. And again, the idea is that always there are multiple types of regularities at our disposal, and an efficient behavior would be one where we are going to rely on more efficient sources of information and ignore regularities and cues that are less efficient. Now, of course, if we take this seriously, it kind of means that we need to change the way in which we study statistical learning abilities in the lab. We can no longer use those tasks where we isolate one stream of information in a highly simplified scenario. We kind of need to go and start to explore statistical learning abilities in more ecologically valid and more complex scenarios. And as a first step, with colleagues at the University of Toronto, we looked at attention allocation in such more complex environments. So this is work where we now present to participants, instead of, again, just one stream, one visual statistical learning stream, one stream of shapes that appear in the middle of the screen, spoon-fed to participants, we present to them 4 streams of information at the same time, right? This is a very complex visual setting. Participants have literally no idea what is going on, but we constructed the stream such that each of those streams have a different level of predictability. From one stream that is very simple, that actually comprises of pairs of shapes that always appear together, to a stream that is less simple, pairs of shapes but with some noise, to a stream that is even less simple, more noise, to a stream that is random. And then we quantify using, again, this measure of entropy, certainty, quantify how much uncertainty there is at each stream, at each point in time, given, given the shapes, the information that participants got until this point in time. And what we saw, both using search trial data and using eye tracking data, is this very interesting phenomenon. What we see is that earlier in training, participants attend to more simple parts of the input. But over time, over learning, attention gradually shifts to more and more complex sources of information. Now, of course, this is just a very simple step. Needless to say, this setting is still highly artificial, but I think it is a first step trying to kind of embrace the complexity of real-world inputs and kind of try to understand what is going on when we look at statistical learning in more complex inputs that actually simulate what we need to do in order to gain high-level cognitive behaviors. But of course, there are many, many challenges that this approach still opens. The first is that we kind of need to now have an alternative new approach for measuring statistical learning abilities. Again, no longer using those visual and auditory statistical learning tests, which, don't get me wrong, I use them for a lot, and in many ways I developed some versions of them, etc. But I believe that they are not giving us all the information that we need. Instead, what we can do is either run an analysis of the cognitive outcomes themselves from a statistical learning view, much like what we try to do or try to do now with reading, taking into account the different types of regularities that exist in different domains. But we can also try and do this by actually developing a new set of more ecologically valid artificial statistical learning tests that actually look at behavior in more complex settings. And as always, even if we go through the methodological challenges, we still have many new theoretical challenges that I think this approach kind of highlights. We need to understand, well, what are the relevant available regularities that exist in different domains, and what make a regularity more or less efficient in the context of a given task. We need to understand, well, how learners' behavior actually change as they gain more and more experience in complex real-world environments, not just in the order of minutes, but also in much longer timescales. And lastly, we need to understand, well, what is the overlap versus divergence between the mechanisms that are involved in learning different types of regularities across all of these different domains. Again, taking into account the complexity of real-world environments. And on that note, I just want to thank my very dear colleagues from the Hebrew University, from Haskins Laboratories, and really from all over. And specifically, I want to thank Ram Frost and Louisa Borchertz, who had a huge part in all the work that I presented on statistical learning, the earlier work, and Ken Pugh and Jay Rickel, again, my postdoc advisors, for their immense contribution on the work on reading. And also my funding. I'm available, of course, for questions here and also by email. Always feel free to ask me whatever you have in mind. Thank you for your time.
Okay, thank you, Noam, for the wonderful timing.
Yeah.
So that leaves us sufficient time for to answer questions. So to the all people who attend the talk, feel free to just raise your hand or open your microphone or type up your question in the text box. I guess I would like to start with a question, sort of combining 2 points on your last concluding slide. You mentioned that people's attention or resources to different levels of regularities would change according to their experience. And in the reading research you introduced, you seem to mainly focus on the learners of reading, that is school-age children. So do you have some, so I'm familiar with your research about like testing adults reading, but do you want to sort of enlighten us or put the story together, mentioning like using that as an example in terms of reading? For example, young kids pay attention more to the simple regularity between orthography and phonology, and maybe to semantics too. But can you also share how that is changed through development when we all become when we all become very mature readers? I'm asking because there was the long debate, especially for Chinese reading. I think that debate still holds. That is whether we adopt the similar mechanism as relying on the OPC rule, except the grain size is different, or fundamentally because of the difference of the logographics writing system, people tend to shift, or the focus is shift to be more relying on the regularity between orthography and semantics. So I guess using this new approach to address the own lasting debate, which we have strong view. We have strong view on it, but I would like to know your take using that approach.
Yeah, of course. Thank you for making this connection between the developmental aspect and what we see in the lab in much shorter timescales. I think that the comparison is correct, and I share it. I think that what happens developmentally is that we start as young children kind of focusing on where we can get the most out of that, right? Explicit teaching, of course, helps, right? Instruction, of course, and this is kind of the role of instruction from a statistical learning perspective, kind of to minimize the hypothesis space and kind of focusing us on the part of the input that is going to be most efficient earlier on. So at first, we start by looking at the parts of the input that are most reliable and efficient. And then over development, we are starting to look for information in gradually more and more complex places, right? And we see this both at the level of the mapping between orthography and phonology and semantics in English, right? So for example, this work with the overall sensitivity to orthography to phonology regularities, right? Just the vowel graphing to phoneme, the simplest type of regularities, but then the gradually more later, more subtle regularities that develop, the context-dependent regularities, and also the orthographic to semantic regularities. Right. Now, I believe that when we take then this, we go later and later into adulthood, the regularities become more and more complex. And also they are gradually shifting from the mapping at the single word level, the orthography to phonology and semantics, to the orthographic domain. That is what readers try to do at some point, is to come up with efficient predictions regarding the orthographic information that is coming in, right? And this is the types of measures that we're trying to develop now, right? To work with now, right? Both the measure of lexical conversion that I showed, but also many measures from language models that essentially try to capture predictability of incoming orthographic information. And so for older readers that essentially already have a quite efficient way of getting from print to sound and meaning, they can further facilitate their information uptake in longer texts by actively and efficiently predicting upcoming orthographic information. So I think that this is all very consistent with the idea that we look for information in more and more complex places of the input. Right. Now, going back to Chinese and cross-linguistic differences, I mean, of course, you know way better than me. To me, it's I think that there's enough evidence out there, please correct me if I'm wrong, that phonology matters regardless of the language. Right? Phonology is kind of a building block, right? Reading is parasitic on speech regardless of the language in which you operate. But I think that it is also true that the solution the different writing systems adopted can change the organization of the reading system, right? So if you have more complex orthography to phonology regularities, you might tend to rely also on other sources of information. When we think about individual differences, it may be the case that in language such as Chinese, the relative contribution of orthography to phonology and orthography to semantics to reading skills is going to be different than in English, and this is going to be different than in a very shallow language such as Spanish. I will say that I'm very much interested in just running this study. It is very simple, right? We just need to quantify orthographic, phonological, orthographic, semantic regularities in Chinese, which we can do quite easily. And I know that there are already quantifications, and we can see whether we need to modify them in any way. And we need to run those very simple word reading tests and see what we get. So I'm all in if anyone's interested. You or anyone's interested. I think we can do this together.
Sounds very interesting. Yes. before I have other questions, but I want to give time to others. So if you can read the text. So there is a question in the text box asking, how does statistical learning ability develop? Is there any way to enhance the ability of statistical learning, especially for L2 learners? You probably get that a lot.
Yeah. We have a PhD student actually working on that, trying to see what statistical learning abilities can be trained, and there's some other literature as well. I have bad news and good news. The bad news is that I don't think that there's a good way of enhancing statistical learning abilities. It seems to be a quite stable characteristic of the individual, meaning that given a certain input that someone's going to get, it's very hard for them to be able to be more efficient, to be trained in extracting this information better. We do not see evidence for that. Or at the very least, even if we are able to train them on something, their ability to generalize this and to be able to pick up new information from a different input is very limited. There's not a lot of generalization. So this is the bad news. The good news is that I do believe that this statistical learning approach kind of tells you what you should be doing in terms of instruction. Because instruction essentially can be thought of as a way of manipulating the input, right? So, our eventual goal is to understand what is the given profile of a learner. It can be a kid or it can be an L2 learner. Understand what are the types of regularities that they are and are not sensitive to, and then kind of tailor the input in a way, shape the input in a way that is going to be maximally efficient for them. Because even if their statistical learning abilities are stable and are not going to change, there may be an input that fits better with their knowledge and with their statistical learning abilities. So we have some attempts to do that. Of course, they are very early. Mm-hmm. But this is my take, that the statistical learning abilities per se are stable, but that the input can be changed in a way to better tailor the abilities of a given individual and the experiences of a given individual.
Yeah, I can add something to it that we had some data from foreigners learning to read Chinese. And the data seem to show that no one probably have heard about it. If the learners went to the formal class to learn Chinese, their statistical ability measured in those typical like triplet segmentation tasks did not predict how well they perform, while how well they learn, pick up new learning to read Chinese characters. For those who did not go to the formal class, they may their statistical ability predicts how much they pick up Chinese orthography through daily lives. So the ostensibly paradoxical finding actually suggests that statistical learning is important, or finding regularities is an important ability for you to learn a new orthography. But if you have instructions, so if the teacher is doing the right thing, right, the classroom is helping you, then you are provided with the information, with the structure embedded in the orthography, then even you were not born with a very good sensitivity, but you have a good teacher, you have good materials, then that disadvantage can be alleviated. I believe probably people who have better statistical learning ability may still pick up the class materials better, but at least you are also in the class. You are not like totally disadvantages. You are not totally on your own. But if you do not have any structured information being digested or provided to you, then you are on your own. Then if you are born with a better sensitivity, maybe it's an easier task for you. So that piece of information may speak something to it.
Yeah, definitely. That's a very optimistic take. That's great. That's a great finding. And I think it shows that, instruction, of course, is important, and instruction can alleviate some of those differences that we have. So yes, an ideal instruction can really minimize the hypothesis search in a way that would really, really bootstrap learning.
Yeah.
Of course, not everything can be explicitly taught, and there will be some individual differences, but we want to alleviate them as much as we can. So that's a very, very optimistic finding that I'm really glad to hear that.
Right. And just to be clear, I'm not saying statistical learning would become not important at all if you are in a classroom. But I'm just saying that compared to others who are not provided with the structured materials, then you will be better off. And who benefits more from such structured materials might be those who will be less capable or less efficient of getting the regularities.
Yeah,
I guess that's indeed a positive take.
Yeah.
Yes.
Can I ask a question?
Of course, Gary, please.
Thank you, Noam, for the very interesting talk. So I have a question regarding statistical learning in syntax, especially in second language learning, right? So now, well, take me, for example, like I still sometimes say, John go to school, well, bit dramatically, right? But in English, you need this third person agreement. You put S there, it goes, right? But a lot of Chinese learners would just make mistakes in agreement. But if you look at the input, really, there's a lot of regularities there in the input. But why would Chinese learners and learners from other language backgrounds to not pick up the agreement from the input? Do you have any comments on that question? I think this is a very practical question, actually.
Yeah, that's a great question, actually. I don't know the answer to that, and I can speculate a little bit, and I'm happy to speculate together with others. So one option is that, and this is, of course, a more controversial option, is that there's given some shared representation of syntax in your native language and in your second language, there's some interference, right? So if you come from a language where there's no agreement, and this you got a lot of input to that, given many, many years to your first language, and it's in a system where the representations are shared between agreement in a first language and a second language, getting now, thousands of exposures in the second language is nothing compared to the millions of exposures that you got in your first language, given shared representations, right? But this assumes that the statistical learning, in terms of this particular example, operates in some level, right, on something that is shared in terms of representations, which is, of course, a big question that I don't know the answer to. The other thing that, I've been thinking about in terms of agreement specifically, and statistical learning in terms of agreement, is that this really interesting notion of redundancy, right? When you say John goes to school, the goes, the sound, in terms of the meaning, doesn't give you anything. It's completely redundant in English. It's something that was, English chose a system that is in some way, like from an information theoretic perspective, it's actually not optimal, because there are multiple cues there that give you the same meaning. And it seems like those particular cases are where some second language speakers struggle. And it may not be necessarily because of a bad thing, in quotes, of course, but it's actually because it is not something that gets you to the message correctly, right? So perhaps as second language speakers, we are just having troubles learning things that are more redundant in the input. So that's something that, there's an interesting literature about redundancy in language, and the role of redundancy in first versus second language learners. And I think that this is one of those cases where statistical learning really need to touch with this literature, right? Because at the end of the day, you can think about redundancy from statistical learning perspective as a case where you have multiple cues that are essentially overlapping and not necessarily giving you more information, right?
Yeah, I think the kind of redundancy, the semantic interpretation thing is interesting.
Yeah.
I'm not sure about the kind of L1 interference though, because for example, like I learned Japanese a little bit, which I forget already. But no, despite the word order difference, for example, I don't make mistakes in the kind of word order in Japanese, right? So that means actually I can quickly pick up the word order regularity in Japanese as L2, despite the word order difference between Japanese and my L1 Chinese. But
yeah.
So this kind of redundancy thing and this kind of the lack of semantic or meaning of these agreement markers, that kind of reminded me of the visual tasks and the auditory tasks introduced at the very beginning, right?
Yeah.
So how good these measures are for measuring kind of statistical learning, because when I'm listening to these syllables, I don't need to make sense out of them. And so does that mean then, no, it's not a good measure of a person's statistical learning ability?
Oh, yeah, I definitely agree with that. I definitely agree with that. I think that those measures, and don't get me wrong, I use those measures and I still do. In some cases, they give us good information, and they are good in the sense that they can produce reliable signatures, right? So we don't know now how to produce measures. Denise has been doing great work on that. So we can produce reliable measures. And there are, of course, interesting manipulations that we use. We can use those specific tasks to test. But when it comes to overall individual differences, I think that those tests are limited, and they don't capture the things that are relevant and important and theoretically interesting as much as potentially other tasks. So for example, for me, really the tasks, when I think about the next generation of statistical learning tasks that, we kind of try to develop now. So you can still use artificial tasks, but try to, again, go to tasks that are a little bit more realistic. And perhaps try to capture things that are relevant in real world lives. For example, your ability to overweigh reliable information, efficient cues, and underweigh cues that are not efficient, right? But of course, this would mean that we can't use those tasks anymore. We need to use tasks that look very, very different, that actually have multiple cues. Or going back to your question and this redundancy idea again, we need to kind of use tasks, develop tasks that have this notion of redundancy and see how they behave, right? So I still believe that there's a lot there. I mean, don't get me wrong. I love artificial language studies. I love artificial orthography studies. And I think that they have a lot of explanatory power. But we need to be careful not to take a very simplified, naive task and kind of say, well, this is statistical learning abilities. And I think we as a field, unfortunately, kind of did that for a while.
Great. Thanks a lot.
Thank you for the question. Yeah.
I saw two questions in the text box. One is more specific, technical. That's from Cynthia, about how you get the slope scores from individual participants. And the second question, I think it's very broad in terms of like maybe some suggestions in terms of how to apply electrophysiological techniques, which I assume is like ERPs or EEG type of frequency analysis. It has been used in SL research. So maybe to combine that with second language learning, can share whether you have any suggestion. But maybe the first question about the technical analysis, which I think may be useful for many people in the audience.
So sorry if that wasn't clear, first of all, and thank you for the questions. This is actually the slope scores there are actually from separate logistic regression models fitted on the data of each child. And of course, the question is why we didn't use logistic mixed effect models, and we actually looked at the random slopes. The answer for that is that apparently the ones that are based on separate regression models are slightly bit more reliable and valid. And we think that the reason for that is that the mixed effect models apply too much shrinkage, right? They take individuals that are essentially really on the edges and they kind of shrink them too much towards the mean. The other challenge is that in our particular data, I didn't really go into that. I presented this as if we have 400 kids, just, didn't really talk about the properties. But in fact, these kids are not normally distributed, which kind of violates some of the assumptions with the mixed effect models. There are some kids there that have reading disabilities. There's a subgroup of 120 kids there that have reading disabilities. This is also the sample that we then follow up with in the intervention study, and the rest are more continuous. So by using those mixed effect models, I think that the shrinkage that was applied was not really proper. I hope this answers the question. The second question about electrophysiology, and specifically in the context of second language research, I think that there is a very interesting literature about applying EEG, MEG, trying to get some signatures of statistical learning. I think that there has been some great development. A lot of it actually comes from really interesting work trying to see what happens actually before a stimulus comes up. So essentially the preparatory signal, oscillations mostly, less ERPs, more oscillations, showing that there's some oscillatory signal before a predictable versus an unpredictable comes up on screen. And I think that now when you think about second language learning or language processing, generally speaking, I think that this is potentially very interesting two literatures to combine. So to see whether the signatures that we see in more simplified statistical learning tests, they actually have to do with the same types of signatures that we see in more complex real-world settings. And what is the overlap there? And what makes the signatures more or less similar to one another? So I think for me, that's thinking about how to use electrophysiology, that's potentially interesting thing to do. I'm sure that in the crowd, there are people who know way more about electrophysiology than me. So please feel free to jump in and, tell me that I'm wrong or, come up with great ideas.
And there's one more question in the text box.
Well, I see that the question is, where does the construct of statistical learning ability situate in the architecture of human cognition? And do we need to control for working memory in experiments studying statistical learning ability? I think that's a great question. I think that indeed, some of those, some measures of statistical learning indeed correlate with working memory. The correlations are not huge typically, but we do get stable correlations of about 0.2, 0.3 between measures of statistical learning and measures of working memory. Not just working memory, by the way, also general intelligence have slightly lower, but still robust correlation. If we are doing those type of correlation studies, of course, yes, we need to control for that. I think that we also need to remember that in the real world, there's no statistical learning without a bunch of other cognitive constructs that come into play. Working memory is definitely one of them. We can't do any statistical learning computations if we don't remember. We don't have working memory. And attention, I think, is the other one, right? We can't really do statistical learning computations if we don't attend to the relevant parts of the input. But then we also see that what is relevant and what isn't relevant in the input kind of shapes our attention, right? So the statistical structure of the input shapes attention, and attention shapes statistical learning. And I think that the same is true for working memory. The statistical structure of the input impacts working memory, and working memory impacts what we can and cannot learn from the input. So in that sense, that's a very important integration to be made. We need to integrate studies of statistical learning with studies of other domains. And this is, again, another argument that has been voiced by some people now in the statistical learning world. We shouldn't treat statistical learning as not as a black box, but also not as a separate construct. Statistical learning always interacts with other domains. Mm-hmm. So I think that's a great observation.
Mm-hmm. I think something relevant to this point is that from our experience, if you are doing the behavioral measurements, so in the end, you have the reaction time as an index of how quickly or how, for example, take the very classic so sort of like implicit statistical learning task, which is the serial reaction time task. And we found that so from some indexes, it seems that people have learned the regularities embedded in the key sequence. But people may have different tendency of how much they are willing to go faster. That is, they have some prediction. They might have extracted the rule, the rule in their mind. Oops, sorry. They might have the structure in their mind, but they might not be equally willing to use the prediction. So do you have any insight on that? So it's like some people,
that's
they might
super
have the
interesting.
rule, but they don't want to force themselves to press the key quickly.
That's
while
super interesting.
some others, they do it very quickly.
That's super interesting. And this is essentially a whole new dimension of individual differences that we kind of ignore. I think that for that, I'm a big proponent. I didn't present any more on that today, but I'm a big proponent of generative models to analyze data, especially from those type of reaction time tasks where we actually get a lot of tracks. Oh, by the way, also neurobiological measures, etc. So think we can imagine, let's say, a generative model, let's say a Bayesian generative model, just because it's easy for me to think in this framework, right? Where we use the reaction time data, but now we include also some parameters that actually have to do with not just how good you are in actually picking up the structure, but also how willing you are to actually implement what you've learned to produce those responses. And this can vary along individuals, it can vary along time in the tasks, right? And this can kind of separate out individual differences in a whole new way that we didn't think about before. Yeah. So again, yes, I really like this idea. I never thought of this, to be honest. This tendency of people, like, given that they utilize something, how willing they are to actually take the risk and implement it and predict, right? In a way, it is risky. It's very cool. Yeah.
Yeah, we should talk more on this.
Yeah.
Have some data too that might be relevant.
Sure.
But okay, so there's one more question, and probably that will be the last one before the time rounds up.
Sure. So the question is about redundancy in language, like the goals example from before. Do beginners tend to ignore learning these redundancies, even though the regularities are reliable and clear, as long as communication is not hindered? Oh, that's a very interesting question. I think it is a study to be run. I wished I knew the answer to that. There's some work I can send me an email, I can send it around. There's some work by Shira Tal and Inbal Arnon. They looked at redundancy and the role of redundancy in increasing learning outcomes in children and adults. These were artificial language experiments where they had or did not have those type of redundancies. And they wanted to see whether children that are presumably have less robust learning systems at this point versus adults use this redundancy differently. And what they showed is something along the lines of your prediction. So essentially, they show that, yes, the children are having troubles identifying some of those redundancies, but they also actually show that having this redundancy really helps them pick up on structures in the language. That is, redundancy seems to be beneficial for learning, right? Having this redundancy, having those multiple cues is good for learners, child learners specifically. You now ask a very interesting question, like, how we as learners at different stages are going to treat those redundancies. And my prediction, I think, fits with yours, that we are at the beginning, we're going to have some trouble. It's going to help us to get those redundancies in picking up on something, but we may ignore them, right? We may ignore them, as you say, as long as communication is not hindered. That's exactly the right way of saying that. Yeah, very interesting prediction.
It might be relevant to someone's working memory span too, right? So it's like you have more resources, or you have more attention span, or a bigger working memory capacity, then you might as well just pay it notice, or you store, or you have the information in your mind with more complex representation, while if you are limited, then the influence from redundant information might have different impact on the performance.
Exactly. And this is, that very interesting predictions to be thought of. Yeah.
Thank you so much. Well, I personally have learned so much like every time because I am familiar with some of the work, but I really appreciate the opportunity to listen to Noam again. And I hope you all enjoy the talk as much as I do.